Hello everybody and welcome to NPTEL online certification course on semiconductor devices for next generation field effect transistors, a physics perspective, and this is lecture number 53. And the lecture topic is Introduction to Compound Semiconductor Materials and Devices. So, in this lecture we will be actually covering the areas of compound semiconductor, and the following are the sort of a class wise segregation of the areas in which we will be looking into. We will be introducing you to the compound semiconductor materials and then materials for high speed devices and circuits, and then we will concentrate on HEMT, which is one of the important devices where 3-5 semiconductor is being used, known as high electron mobility transistor HEMT. We will look into its modeling and simulation, and then finally concentrate on the FinFETs and maybe gate all around devices using 3-5 semiconductor. So, the whole of this lecture series on compound semiconductor starts from materials, goes to devices, looks into modeling and simulation, and finally end up in a field effect transistor concept. So, that was the general flow of this 3-5 semiconductor, and maybe we are deviating from silicon, which is a standalone semiconductor, to a compound semiconductor for the first time in this lecture series. First class we will be actually looking into, we will be introducing into some compound semiconductor and then look into direct and indirect band gap semiconductors. Then compound semiconductors on silicon we will have a look. What are the various characteristics of compound semiconductor, and then maybe we will look into few of the applications of compound semiconductors. So, let us introduce to you the compound semiconductors. Now, as you are aware that currently with this semiconductor mission underway, there has been concentrated effort both from industry as well as from the government as well as academia to move towards semiconductor sort of the semiconductor enabling our ecosystem, semiconductor ecosystem with self reliance, within which there are two basic areas in which work is being going on. Apart from many other multitude areas, two important areas. One is the silicon, which is always has been always discussed with you for the past few weeks. There is another field which is very important and has very niche application areas, and this is known as compound semiconductor. Typically, all your power devices where you require very high power, unlike silicon, silicon does not allow you to go for those high power devices where you require very of the order of few kilovolt, maybe the breakdown voltage, or you require currents of the order of few amperes. Silicon won't be able to handle that, and that is where the compound semiconductor comes into picture. So, let me first of all distinguish between semiconductor, compound and silicon. So, the compound semiconductor, as we know, is a generic term between whose conductivity lies between a conductor and insulator, right. So, that is what is written in the first statement or the first block of my slide. Now, silicon, you are all aware of, the main application of silicon was that it's an intrinsic compound, it's a monoatomic compound. So, basically silicon is made up of sort of a catenation. We define this to be as catenation. This is silicon catenation, where each silicon is bounded with 4 silicon nearby atoms, and therefore, since silicon has got a valency of 4, which you therefore will see in this if you look, this is group 4 element. So, this is group 4 element, and therefore, it has got 4 valency shell, and this concept is known as catenation, right. And this catenation allows you to do a quite an arrayed form of architecture in terms of silicon, which is also possible in case of carbon. So, both carbon and silicon show you this catenation where each valence shell of silicon is having a covalent bonding with nearby silicon or carbon atom respectively. However, in compound semiconductors, it is made up of two or more materials, and these 2 or more materials generally when we say then for example, we say this to be as a 3-5 compound semiconductor, which means that it is made up of group 3, it is made up of group 3 plus group 5 element, right. We define this to be therefore as a 3,5 compound semiconductor, and that is the second point which you see, that is made up from 2 more elements, then we define that to be as a compound semiconductor. Now, if you look at the chart below, then you can see that purely this semiconductor here broken into simple and compound. Simple will have silicon and germanium. We have already been dealing with it for the last large number of lectures, whereas in compound you have 3, 5, we can also have 2, 6. 2, 6 is this and this, right. This is 2, 6. So, it is basically amalgamation of group 2 and group 6, and this is an amalgamation of group 3 and group 5, right. And that is, so this is basically group 3 and 5, which has got gas or gallium arsenide. So, this is gallium plus arsenic here, and then we have indium phosphide. So, I have indium and phosphide here, right. You have then gallium nitride, gallium plus nitride here. So, you have GaN, right. You have indium phosphide and you have gallium arsenide. This is group 3, 5. Now, if you go to group 2, 6, which is this and this is group 2 and 6, group 2 and 6 means this, and group 6 means this. So, it is basically zinc sulphide, sulphide will be here, and then zinc selenide will be here. Then you will have silicon carbide, right, silicon carbide you will have, and then you will have silicon germanium, right. This and this can also be compound semiconductor within group 4. So, this is group 4 element. So, you can have therefore 3 types of semiconductor compound which is available. One is 3, 5, 3, 5 will have gas, gallium arsenide, indium phosphide and gallium nitride. Group 2, 6 or group 2, 6 means of the periodic table column number 2 and column number 6, we have zinc sulphide and zinc selenide, and then within group 4 you can also have compound semiconductor, for example, silicon carbide and silicon germanium compound semiconductors. Now, I just not told you where they are most effectively used. Most of the compound semiconductors are used for power devices, right, where the power requirements are very high. Now, most of the power semiconductor devices are the fundamental blocks for any power conversion systems. So, if you want to have a power conversion system available with you, let us suppose you want to have a power conversion, then you need to ensure that the system losses, right, the system losses and the speed, they are not compromised in no manner, which means that you should be able to switch from on to off state at a very fast pace, that is one. And second thing is you should not be losing power, because then efficiency of your power converter goes down. So, these two characteristics are very well taken care of by for example, a GaN device very well. Now, as I told to you, there are 2 very important parameters which we will be looking as we move forward. At this stage I am just giving an initial guess, and the one is the breakdown voltage and another is the on resistance of a device. We will come to that later on as we move ahead. However, silicon has got a basic limit. That is the reason why compound semiconductor came into picture, was that basically its band gap is limited, right. For silicon the band gap is limited, and that is the reason, since it is limited, you cannot therefore have electron hole pairs being generated for very large values of input power, which is possible in case of 3-5 semiconductors. Now, typically there is an increasing demand for a wide band gap material, right. For wide band gap material there is an increasing demand whose band gap should actually exceed 3 electron volt, more than 3 electron volt, and even ultra wide wide band gap material where it is greater, whether is greater than 4.5 electron volts, right. Now, among the large wide band gap material, you will have gallium nitride has come out to be a major resource for all practical purposes. So, typically we are looking at gallium nitride as a sort of a alternate material for compound semiconductors. Okay, so this is it, and we'll take at the properties each one of them as we move ahead. Let's look at direct and indirect band gap semiconductor. Now, if you remember your EK diagrams, right? EK energy versus momentum. So this is E versus K, and if you look very carefully, it was sort of a parabolic curve which we were getting, right? Because energy was k square times available to us, and therefore, when we plot a EK diagram both in the conduction band and in the valence band, I get for the conduction band a positive slope, and for the valence band a negative slope available to us, right. Now, there are two types of material where so one is known as the direct band gap material, right. What is a direct band gap material? Is very simple and straightforward. In the direct band gap material, the band occurs at the same value of momentum, right. The minimum and the maxima of, or the minima of two bands will be at the same momentum scale. So, if you look at the picture to your left here, for example, right, this is my conduction band and this is my valence band. The minima of my conduction band, right, and the maxima of my valence band are just on the same momentum scale, right. This is the momentum scale which you get, which means that the momentum exactly the same, the energy of the particle same, and this is known as direct band gap, which means that they are one over the other and not in K. Whereas, if you look at the indirect band gap material, the maximum energy of the valence band and the minimum energy of the conduction band, they do not lie on the same momentum space, but they are shifted from each other. So, you see this lies somewhere here and this lies somewhere here, right, and therefore, the difference between these two is basically known as the band gap, right, the band gap which you see. So, therefore, if for example, in the first case in the direct band gap material, if the electron has to travel from conduction band so to the valence band here, right, it releases an energy, right, but that happens with just change in energy, there is no change in the momentum space. You get the point, which means that its velocity effectively remains the same, but the energy, kinetic energy, falls from a high value to a low value, and there is a recombination taking place between electron and hole. Whereas, if you look at the right hand side between the direct and indirect band gap material, for an electron to come from this point to this point, there has to be radiative energy coming out as well as some coupling energy. So, it will not be just the band gap which will come out. So, what might happen is that this reaches to a value intermediate stage, and from there it reaches to this value here, thereby releasing some extra energy, because this is changing the momentum as well, right. And therefore, direct band gap and indirect band gap materials will always have the amount of energy released will be different for both the materials in that case. Now, if we go one by one and see what are the various materials which are involved in the direct band gap and indirect band gap material, then let us go one by one and see how typically the values are sort of maintained in case of direct and indirect material. Now, let us look at the elemental material first, which is silicon, we have germanium, and then we have tin, and we have carbon, right. Now, out of which, if you look very carefully, germanium, because we are the best we know is for these things. For silicon and germanium, it is basically an indirect band gap material, right, and the band gap at 300 Kelvin is given by this value 0.66 electron volts and 1.12, which is relatively small in terms of energy, right. Now, so if you remember that energy was equals to h nu, right, and therefore, this is h c by lambda. So, what will happen is that I can plug this value of energy here, and from there I can get the value of lambda of the light which will be emitted. So, if you give that much amount of light available, I will be able to indirectly jump an electron from valence band to the conduction band. Let us look at carbon, and this is where interesting thing happens. If you look at carbon, carbon is an indirect band gap, agreed, but its band gap energy is very large. It is 5.47 electron volts, which means that in order for an electron to move, not an electron, but a particle to move from valence band to conduction band, the amount of energy required in carbon is very, very large, right. And it might even happen that before being promoted to a conduction band, the meltdown of the carbon can take place, or the physical properties of the carbon material can take place. But that is not true for silicon and germanium, right. Okay. Now, with this, let me come to group 3, 5 semiconductors, right. Within 3, 5, I told you I have got gallium arsenide, right. We have indium arsenide, indium antimonide, gallium phosphide, gallium nitride and indium nitride. So, we have taken 4 out of it, and it has been taken from this reference, if you can see properly. And interestingly, you see, as you move from elements to a compound 3,5 semiconductor, most of them except gallium phosphide is basically a direct band gap material, which means that if you take gallium arsenide, indium arsenide, indium antimonide, gallium nitride and indium nitride, they are all falling in the line of sort of a direct band gap material, which means that in all these cases the change will be nothing to do with the momentum change. It has to do more with the energy change taking place from a lowest from the conduction band to the highest to the valence band. And within that also, if you look carefully, gallium arsenide has got a band gap of 1.42, which is very close to, if not exactly equal, close to silicon, right. So, you can take a gas and as have it, but then it will not work because it is basically indirect. This is a direct band gap. You will look at indium arsenide, it is 0.36, right, and it is very, very low. Indium antimonide has got 0.17 electron volts, and then let us come to indirect. This is an indirect one with 2.26, and within the direct, gallium nitride is 3.36 and indium nitride is 0.70, right. So, one thing is for sure that for example, if you take gallium nitride, since the band gap is relatively large, the amount of energy and therefore, the power handling capacity of gallium nitride is relatively better as compared to any other device as far as power devices are concerned. If you are looking at group 4, say for example, silicon carbide, it is basically an indirect band gap material with a 2.99 electron volt. This is group 4, 6 if you take, I have got zinc oxide, cadmium silicide and zinc sulphide with band gap of 3.35, 1.17, 1.70 and 3.68. Now, you see quite interestingly, zinc sulphide band gap is very close to again gallium nitride devices, but then we can say that we can interchange gallium nitride with zinc sulphide. Easier said than done, because other properties of material apart from the band gap comes into picture when you are actually devising a high mobility or a high transistor devices. The mobility also will come under question. We will look into it as we move ahead in terms of understanding the whole problem with this direct and indirect band gap material. Further, to add some characteristics of the device of gallium nitride. Now, gallium nitride also has an exceptional property that it has got a very, very high critical electric field, and this is of the order of 3.3 megavolts per centimeter, right, and also has a very large saturation velocity. So, basically it means that I can operate it at a relatively higher voltages, and since my saturation velocities are larger, I can effectively give a larger potential on the drain side and still not reach saturation, because the saturation velocity is relatively large, right. Every time I am trying to push this not only to the material, but also the application side. So, if you look very carefully, if you look at GaN devices, power devices, they have very low on resistances, and therefore, the currents are relatively high, and it also provides very low losses. Conduction losses are very, very low. And the losses are low and not only that, the losses are low, but they have a good saturation velocity. So, these things are important in that case, and if you look very carefully, the rate at which this electron saturation takes place is approximately 2.5 times that of silicon. So, relatively fast, and therefore, switching speeds are not compromised in case of gallium nitride, right, and therefore, you get a minimal loss, thermal loss in case of gallium arsenide. Now, typically we will come back to this when we come to circuit, but typically gallium nitride based devices are now divided into three parts. The first part is basically known as a low voltage device. For example, low voltage devices whose maximum VDS max is around 200 volts, 200 volts, and they find in many utility in DC converters. We will also find in motor drives, then solar converters, and so on and so forth, right, depending upon the application. So, this is basically a low voltage or a medium voltage design, low voltage or medium voltage which we get. We also have high voltage devices. Let me rub this portion so that it is visible to all of you. So, then we have these high voltage devices, and whose value typically ranges VDS max is around 650 volts, right, and they are generally used in industrial converters. For example, servo motors also, where the current drawn and the voltages are relatively very high as compared to a traditional device. They are also used in consumer electronic adapters, right, and class D amplifiers, and data centers. So, you have a low voltage GaN based device, we have a high voltage GaN based device, and we have the last part is an ultra high voltage devices, and these have VDS max almost of the order of 1 kilovolts or even greater than that. Currently, we do not have very large number of ultra high voltage GaN based devices, but the highest which is commercially available to the best of my knowledge is around 900 volts devices are already available, and they are used for photovoltaic inverters and so on and so forth. Now, typically if I draw a graph and show you what is the range at which these individual devices work, we can go ahead and do that. So, if you let me first of all remove this, erase all the ink, and then we will see what to work on with. So, on the y axis, if we plot the VDS max which we see, then we go for 600 to 900, right, and then we go for 1 to 3 kV, and then more than 3 kV if we plot on the voltage range, more than 3 kV if you see. Then basically from here till this much point, most of it is basically a GaN based HEMT, right, on silicon. You can also have it. Then you have then if you start from here till here, you have silicon carbide MOSFETs, right, and then you also have at this stage GA203, which is gallium oxide based designs, right. Where do you use GaN based HEMTs? You used for photoelectric chargers and electric vehicles, right. Typically this is the range which you use for silicon carbide automobile charger, four-wheeler charger. For gallium arsenide, it is basically rail and power infrastructure. So, typically this is the range at which we are talking about more so, more or less in the same range, but some corrections need to be done at each and every point in this case. Now let's come to the material properties of these semiconductors, compound semiconductors. So gallium nitride has a band gap of 3.39. I will be concentrating more on gallium nitride and gallium arsenide. 3.39, it is 1.42. And if you look at saturation mobility, though gallium arsenide has got a lower band gap, if you look at its electron mobility is relatively very large. It is 8,500 centimeter square per volt second as compared to gallium arsenide of approximately 1,500 centimeter square plus per volt second. And it has got a static constant which is very relatively very high, and this is about 12.9, which you look. And let's look at the saturation velocity. They are almost the same for both the cases. However, and that's where many things work positively for gallium nitride, the critical breakdown voltage is 3.3 as compared to 0.4 for gallium arsenide. Right. So you can understand that typically the breakdown works at much higher voltage in case of gallium nitride as compared to gallium arsenide. Now, so the active material across which the electrons will be flowing will obviously be compound semiconductor, but the substrate material you also need to choose over which you can grow the gallium nitride or gallium phosphide or indium phosphide material, right? And typically which people use is sapphire, silicon carbide and silicon. Now sapphire is most used material, it's good quality and most commercial wafers are available, but however it fails on poor thermal conductivity. So you typically have hotspots being generated at individual places. If you look at silicon carbide, it has got a low lattice mismatch. The reason being, if you look at silicon and carbide, both silicon and carbon are group 4 element. Catenation is very good, and therefore there is low lattice mismatch. So there is no concept of traps being generated. It has got a higher thermal capacity as compared to sapphire. Uh, let's look at the last candidate. It's got a high thermal conductivity, and therefore there is typically no probability of formation of hotspots within silicon itself because of its high thermal conductivity. Large area is available, and the cost is also relatively low because silicon technology is a very mature technology in terms of production and deliverable, and that's the reason you will automatically have a much better mature technology in case of silicon. So let's come to the characteristics of compound semiconductor. Now, when you look at silicon, when you scale down the device per se, we do have a problem that when you scale it down, the channel length reduces, current increases, and therefore I square into R, which is the power, goes on increasing, right? The power dissipation goes on increasing, and that's the problem. But when you come to compound semiconductors, the electron mobilities are relatively very large as compared to elemental silicon. For example, if you look at the column number 2 here, electron mobility is 8,000, this is 1500 centimeter per volt second, which means that the electron mobility in gallium arsenide is 6 times approximately or approximately 5.5 to 6 times larger in case of gallium arsenide compared to silicon, which means that for the same dimension of the device MOSFET, I would get approximately 5 to 5.5 times larger current in case of gallium arsenide. So the current handling capacity is much better in case of gallium arsenide, right? If you look at the electron effective mass therefore is much smaller in case of gallium arsenide compared to silicon, and this directly comes from EK diagram. EK diagram is much steeper in case of gallium arsenide compared to silicon, and that's the reason you have a better device, right? So let's look at the characteristics of silicon compound semiconductor. What we see here is that as the material changes, you see the mobility has actually become 4 to 5 times larger. If you look at gallium arsenide, its mobility is 8,000, whereas the mobility for silicon is around 1500 centimeters square per volt second, and that comes directly from the effective mass. Effective mass is basically the value is basically given by, if you remember very carefully, d2e dk2, right? Remember, and this comes from this formula, and so more is the steeper nature of the curve, lesser will be the silicon. So just to recapitulate what we learned about this lecture is that we learned about the basic difference between a elemental semiconductor and a compound semiconductor, direct band gap and indirect band gap, then looked into the material properties of compound semiconductor and silicon. Once we have done that, we were able to compare the two, and we saw that gallium arsenide has got a relatively larger mobility, larger breakdown voltages compared to elemental silicon. And that was the advantage of compound semiconductor, and therefore its application in power devices, converters, DC-DC converters, and so on and so forth. With this, let us end this lecture, and we will meet with the next lecture. Thank you.